Hi, I'm Mariela Zuniga. I'm here with Gabby Sanchez and Karina Aguirre with the Electric Girls Group presenting our State of the Field report on the implementations of energy storage systems and microgrid technology. I want to use this opportunity to present our conference poster and also talk about the reason why we chose this particular topic. As seen here in the conference poster, this is the outline of our entire project. And our project is mostly based on environmental considerations. As we know, with the threat of climate change and global warming becoming more and more apparent every single day, we see that many energy companies are shifting gears and beginning to invest more time and resources into renewable energy generation projects. However, one of the biggest downsides with the two main renewable energy systems or energy forms, solar and wind, come from the fact that generation is nonlinear and neither is consumer demand for energy. So in this report, we're going to be talking about the various implementations of energy storage systems. And with these findings, we'll be able to analyze how battery storage technology paves the way for microgrid research, which is something we'll touch upon later today too. So with that being said, I wanted to jump into the first case study, which is in Sudan. And unlike the United States, Sudan's large territory and vast distances between communities and cities prevents them from realizing a full-size power grid. The electrical infrastructure has just simply not been established in the way that we know it in the United States. And in order to accommodate the load demand, the city of Naila has implemented a diesel generation power plant that has also integrated wind power and solar photovoltaic with the compressed air energy storage system case. And here in figure 1, we're able to see a simple diagram of this hybrid system. The main purposes of integrating the power plant, the wind farm, the large energy storage system case, and the diesel generation plant was to minimize the electricity generation cost and also to reduce fossil fuel emissions such as CO2 into the atmosphere. In this slide, we can see a diagram of the case power plant system, and it is comprised of the compressor, the cavern, the expander, which are the main components of the system. And as seen from the schematic, case takes in excess energy to compress air that is then stored in the underground cavern, a process that of course generates heat. Then this hot air is used to generate electricity by being sent into a gas turbine seen at the top right of the diagram. With the integration of these two renewable energy plants along with the case system in Naila City, it is observed that greenhouse gas emissions decreased as there was electricity being generated from sources outside the main diesel generation plant. It is also observed that the energy storage system was able to mitigate some of the issues caused by the unreliability of weather conditions. And another energy storage system that I wanted to touch upon is called the redox flow battery system. The main purpose of this particular battery storage system is to further maximize total energy efficiency with various types of renewable energy systems, such as wind and solar systems. And not only this, it can also be applied to non-renewable forms of energy, such as coal, nuclear, or natural gas. And this is accomplished by arranging independent reaction cells in a cascade configuration, which are then configured according to state of charge conditions expected in each cell. And before I get into the next case study, I did want to touch upon what a microgrid is. The definition of a microgrid is that it is a decentralized collection of electricity generation sources and loads that can either be connected to the traditional synchronous grid or disconnected completely and function as an autonomous island. And the reason I bring this up is because many microgrids function well and implement battery storage systems well. I wanted to touch upon the environmental impact of microgrids in a case study in Sweden. And as mentioned before, microgrids are small-scale electricity networks that integrate distributed electricity generation with consumers and potentially with energy storage devices. And the main benefits include offering solutions for electrification of remote areas, deployment of distributed renewable energy sources, and decarbonization of the electricity supply. Here in figure 6, we are able to see that there is a very small amount of renewable energy generation in the bidding area where our microgrid is located. By assessing the climate change impact of the operational changes to the power grid system, we find that microgrids can provide greenhouse gas emission abatements when they are applied in regions where the carbon intensity of electricity is already high, or when they are used for the electrification of remote areas. Unfortunately, we find in this case study that in the short term, microgrid technology cannot provide greenhouse gas emission abatements in areas where the carbon intensity of electricity is already low. From the findings, we know that in order to realize a full understanding of the environmental impact of microgrid systems, we require a long-term approach on scenario analysis. And I'd like to pass it off to Gabby now. Thank you.
Hello everyone, I'm Gabby and I'm going to be talking about the smart grid and microgrid, how they complement and interact with each other. So let's start out by a smart grid definition given by the Smart Grid System Report. So a smart grid uses digital technology to improve reliability, security, and efficiency, and that's going to happen both economic and energy of the electric system from large generation through the delivery system to electricity consumers and a growing number of distributed generation and storage resources. So is that so important, and how is that going to interact with microgrids? So here are some aspects that are really fundamental, not just for this topic, but to understand how microgrids are going to play a role into smart grids. So the first one is that it enables informed participation by customers. So the customers right now are not going to have a passive role anymore. They're going to be protagonists of their own actions, and they're actually going to have a say into what is going to happen to the power around it. Also accommodates all generation and source options. So it could be hybrid, it could be renewable, whatever you want. Smart grid should be able to accommodate those. It enables new products, services, and markets, because we're talking about some hybrid systems. Then you're actually going to be able to have some new market for hybrids, which you don't have currently. It also optimizes asset utilization and operating efficiency. And the reason behind that is because now the market is going to have information about the customers, and it can predict their behavior and fully understand and help on how to make that energy spend more efficiency and decrease the value that the customer should pay. And it should operate resilient to disturbance, attack, and natural disasters, so it should be trustworthy. So let's go next for a diagram of the smart grid. So this one is going to be able to allow us to visualize what we were talking about before. So as you can see, the customer right here is going to be interactive with the service provider, the distribution, the operation, and the markets. And that is going to be a bi-directional way. It's not just unilateral kind of, the customer is just going to be receiving information, just going to accept whatever they can because there's nothing else it can do, but that the customer have actually a say, and the interaction between the customer, the market, the operation, and the service provider is actually what gonna make the grid better. And again, as always, you always have bulk generation, and that can be from coal, wind, solar, and that's one of the hugest benefits. It's not just one kind of generation type, it can be from many of them, and that's what they call the hybrid option. And energy storage devices. So there are many energy storage devices. I think most of us think about batteries when we talk about energy storage devices, but those are not the only ones. I do want to pay attention to the vanadium redox battery, which is Mariella pointed out, because although it has a high initial cost and high maintenance cost, it has a long life cycle and low maintenance, and which is really amazing, it has independent power and energy capacitor, which is going to be great for microgrids. Supercapacitors and superconducting magnetic energy storage are kind of the opposite of each other. One is the capacitor version, the other one is the inductor, and they do have a huge high cost, and the superconducting magnetic energy storage especially requires a lot of space to put that on, so that's not really efficient right now. And they also have flywheel energy storage, which is just a kinetic way to store energy, which is not really great because of high friction losses. As I was saying, this is a kinetic way to save energy, so it's not the optimal, the most ideal one. It also has vehicle to grid, but I want to use just a theory, but what it would be is that it would allow vehicles to store, extract, provide energy to the grid, so they'll play also a key role into the power market of the country. So smart grid and microgrid interactions. So as I was talking before, smart grid is just basically a nice and smart way to analyze the grid so that the customers can also have a say into how their energy is being provided. It's also going to be allowing hybrids and any type of generation any type of sources should be given to the grid, because this grid is going to be made of microgrids. So basically, because this grid doesn't need the shutters that much, and they're always they have the little isolated microgrids, then it's fine they don't all have the same source. And another important thing about this is that any disturbance in the grid, because the microgrid system, you can just disconnect the house or the village or whatever that happened, and then you can just go there and fix that problem. You don't have to get a power outrage for the whole town just because of one house, which is really beneficial.
Hello, I'm Karina, and I will be presenting on our findings on the environmental benefits of microgrid and energy storage technology. To start, one of the major issues concerning today's centralized power plants is the gas emissions they produce as byproducts of power generation. These major sources of pollution originate primarily from coal-fired plants and include carbon dioxide, nitrogen oxides, sulfur oxides, and sometimes even mercury. In addition, these coal plants also produce solid waste in the form of ash from the pulverized coal. And this is truly a pressing issue that affects people as well as flora and fauna worldwide. The gas emissions produced by burning fossil fuels are known as greenhouse gases, which trap heat and make the planet's temperatures rise, overall making the planet warmer. So as greenhouse gas emissions increase, the planet gets warmer. And as we can see on the chart here to the left, the generation of electricity is the second highest source of greenhouse gas emissions in the United States. And it's important to acknowledge the negative environmental impact of said byproducts and how a distributed smart grid infrastructure, particularly one composed of energy storage systems and microgrids, might help alleviate that impact. For this reason, shifting the way our power is generated and distributed by today's current electrical grid needs to be improved upon. As mentioned in the previous slide, the generation of microgrids in conjunction with energy storage systems has shown promising results in reducing gas emissions when compared to the amount produced by traditional methods. By implementing these technologies, we are also enabling the use of renewable energy sources such as solar energy. But because these renewable energy sources produce very intermittent and varying power outputs, the microgrids would need to be paired with energy storage systems to really yield the maximum amount of benefits. And as seen on the graph here, coal and natural gas are still the main sources of energy production, but allowing the introduction of alternative energy systems would decrease our dependence on fossil fuels and ultimately help in reducing a major source of greenhouse gas emissions. One example of this successful shift is demonstrated by the implementation of microgrids by the German Jordanian University in Jordan. The university conducted a study to determine how the campus's carbon dioxide emissions could be reduced by consuming power generated by a microgrid as opposed to drawing electricity from the local utility plant. The microgrid consisted mainly of a photovoltaic system, which consists of solar panels and 2 generators. Over the course of just 1 year, the data collected showed that while the campus operated on the microgrid, only about 488 kilotons of CO2 emissions were produced. To put that into perspective, while using the utility plant to operate, the campus would normally produce around 1,734 kilotons of CO2 emissions. So by simply operating on a microgrid instead of the utility plant, the campus managed to reduce its carbon dioxide emissions by approximately 72% in just that 1 year. The graph here shows a visual representation of this, of the CO2 emissions produced by microgrids versus the utility plant. On a monthly basis, we see that the amount of carbon dioxide produced by the microgrid, shown here in orange, is significantly less than the carbon dioxide emissions produced while the campus operated on the utility grid, which is shown here in blue. And we can also see that there's a spike here in December for the emissions produced by both sources. And this is due to the increase in demand for electricity used to power appliances such as heaters and radiators in the cold winter weather. Regardless of the spike, we can still see that the carbon dioxide emissions produced by the microgrid, shown here in orange, is still less than that produced by the utility plant. So, in other words, when compared to the air pollutants produced by large-scale utilities, the electricity generated from microgrids using renewable energy sources contributes much less greenhouse gases and pollutants since little to no fuel is combusted in the process. These technologies show a truly promising potential in reducing greenhouse gases and many of the environmental indicators that contribute to climate change.